to you, Howard. Thank you.
Thanks, Paul. Thanks, everybody. Welcome to the session today. It was, I must admit, it's one of the sessions that I've battled to plan for the most, but when I finally got it done, it was probably one of the more exciting ones that I've done. And I've had to spend quite a bit of time talking to Veronica, trying to work out, what do I talk about? What do I need to talk about in terms of data citizens and data storage and operations? So I will share with you sort of my challenge. It was quite an interesting one. But remember, we did the essential concepts last week, and we went through quite a lot of detail. And so I'm going to go through it relatively quickly because we did spend most of last week going through it, and I wouldn't want to get stuck on that again. But just for a review, so if there's anybody on the call that would like to get me to explain a section a bit more, then please put your hand up. I'll stop and I'll talk a little bit more. But we first of all started looking at ACID and base, and of course that's where a lot of the changes have come about. And we've seen this move from purely ACID, which is our relational databases, to base. And that's BASE, which is basically available, soft state, constant state of flux, and eventually consistent. Yes, Sheikh, how you doing?
Hi, Howard. So yeah,
yes.
So I didn't get a chance, Howard, to listen to the last session, but it would be great if you can, just do a trial.
Okay, fine, shall do. Okay, great. So we had the processing type. Some people refer to as transaction types, but it's not really transaction types, because here we have a scenario where there are no transactions, and the transactions basically almost happening at a document level, and not so much at a record level. So it's record by record that we go through. Okay, so let's go through a little bit of these examples. Here's the implications of choosing either ACID or base. And with ACID, you have that really strong consistency. And if you've been through that, if you certainly have gone through the book, and we'll share a bit later, called the CAP theorem, where it's one of those questions of choose two, and then the other one you have to put up with and battle with. And consistency is the one that ACID chooses. Queue, if you're having a transaction or you're trying to read data that somebody else is locking, then you'll queue, unless, of course, you use a with no lock, which is okay. But you then got to be careful that you could be reading dirty data. But it can help. The scale up, you tend to scale horizontally, or vertically, sorry, and then base scales out. So with the ACID, you're getting precise answers. With base, there's this approximate. You basically reading dirty all the time, which is interesting. And then so ACID is consistency first, whereas base is availability first. So these are different options, different choices. And what I'd like to say from the beginning is, I don't think it's about having one or the other. I think it's about having both. We should not compromise certain business use cases that require ACID and jump to base. And I've seen some examples of Amazon on Black Friday, or it was Amazon on Black Friday, where we had this interesting case in the beginning where one had something like $200 in your account. You bought 3 books and you still had $200. And people started to get into face some challenges when the account wasn't going down as it should do, and keep up to date with all the other purchases. Okay, so these are some of the different aspects of processing types. And the important thing for me is, if you're in ACID and you're looking for the transactions, you must have the schema. The schema must pre-exist, the table structure exists, and the columns have their typing with all of the rules and the constraints within the business. So when you commit the transaction or when you update the data, if any of the transactions fail, if any of the rules fail, then the transaction fails. So ACID is transactional, base is key value stores. And that was also interesting in terms of anyone really knowing what a key value store looks like. We keep hearing about a key value store, and it's almost as I have a key, I have an ID for a person. I can open the store and I get all the details about the store, about the person. And I'll show you some examples of that as well. Okay, and then ACID, the transactions is, yes, everything is under transaction, whereas base, it's possible. So you almost have to choose and demand to be transaction-based, whereas ACID is by default. Okay, distributed and federated, centralized, this is what it was like for me when I first started in 1985, and I was working for Edgar's, and we had one big mainframe. There was only one location, only one database. Life was easy. We were able to almost bring the system down when the store was closed at 5 o'clock, and on a Friday afternoon or Saturday, and sometimes they opened again on Monday morning. That was the easy life, where you could sort of prepare stuff and get the job done. But of course, sometimes I started on Friday night and I walked out on Monday morning, living the life of a DBA. Then we have distributed but not federated, and notice here we have the 3 different locations. This could be using either replication or mirroring, and whatever updates apply to location A, location B, and location C receive those updates. And we use this for reporting. So, for example, we could have a replicated location C, and we're reporting on this and keeping the reports off location A. So there's a nice way of being able to scale almost in a horizontal way, and you can do this in database as well. Okay. Then when we look at our other architecture types, we could have federated, and notice here we've got location A, location B, location C, and the simplest example that I provide is, let's say you've got 20 million records, you're looking to improve the performance, and you could have 10 million records sitting here, 5 over here and 5 here, and the user view brings us together. Or maybe a better example would be, I could have 3 of the towns in Saudi, Jeddah, Mecca, and Riyadh, and all the Jeddah people, all the citizens that live in Jeddah are in location A, Mecca and Jeddah is location C, and a view brings us all together. And the user who's querying doesn't really know, and you actually teach SQL or whatever it is, you teach it to take a query that's issued by the user and only go and look in the location where the data is coming back from. Now, we have 2 ways of implementing it, either tightly coupled or loosely coupled. This one is almost where the view is hard-coded, and it understands where the different locations are. And in this one, it's loosely coupled, where it doesn't really know where the locations are, and it just scales. And as we add a location C, it's updated by the database. Here's the CAP theorem. Just trying to share with you, for example, if I'm looking for high availability and partition tolerance, then I need to put up with inconsistent data. If I need consistency and partition tolerance, then I can have a scenario where it's not always available. That's where our traditional relational databases sit. And if we want high availability and high consistency, then our partition tolerance is not that good. Okay, so we choose these. This is the Lambda architecture as well. I don't really want to get into too much of that at the moment. Blockchain is a fantastic example of federated. This scenario doesn't depict it entirely. I should take out some of the red ticks here. Whereas if I want to send money from A, I want to send money to my mother or my daughter in Cape Town, I would create a block and I would notify, I'd broadcast this request to do a transaction to the network. And then I could have three, I don't need to have everybody coming back to me, but I could have three people coming back and saying, it's okay, transaction's valid. Let's put it on the chain. And then notice now that's where I get a blockchain from, and then the money moves to my daughter in Cape Town. So a simple example, this is blockchain tends to operate on a technology called distributed ledger, DLT. And so that one looks thin. And then we've had this progression, moving from a data warehouse to a data lake to a data lakehouse. So this was the 1980s where we had the data warehouse. Within 2011, we started to introduce the data lake, where we could have any level of any type of data. And this is sort of where we started seeing the big data, structured, unstructured, and semi-structured data we put into the lake. And then we had processes outside of the lake that would ETL the data into a real-time database, build the reports and marts, or prepare the data for machine learning. And this was done sort of with views that you could build on top of the lake, and you would be able to refresh those views on an ongoing basis. And then we have a data lakehouse where you can see all of this processing and ETL has now moved into the data lakehouse, and then it builds this combination of a warehouse and a data lake. And let me just go quickly enough to show you this is sort of what a data lakehouse looks like, where it has a warehouse for structured data, it has a data lake for unstructured, semi-structured, and you can put in structured. And you have this integration in the shared catalog of where the data is. And then there's this processing layer, ELT, extract, load, transform, big data processing, and then we've got ETL work happening as well. Again, notice the importance of both structured, or all three, structured, semi-structured, and unstructured, and then the batch and streaming mechanism as well. So we've got applications that do a batch extract, and then we've got some of the real-time stuff that's doing devices, web sensors that are doing streaming loads. These are some of the features that led to the data lakehouse that the data lake was battling. It's basically a write once and then read many. So you don't really do updates on a data lake. You're really just trying to, in a way, virtualize the data in some form of in-memory, and then view the data that's on the lake. And if you want to improve or change the layouts, you would just refresh the view or change the view. And so you'd progress. Then we had a data mesh, and that was interesting. I don't know how many people noticed that yesterday with the graph technology that John O'Gorman was talking about. If you are interested in reading a lot of what the work he's done on graph, he felt that this data mesh wasn't really going to work. But I'm not sure about that. I do feel that there's some validity in that, and the validity I see. I must admit this. The data mesh is almost a way of building data products in different environments in data infrastructure, and then the data products are able to share data. I like this diagram from Azure, which is a harmonized mesh. They build blueprints in the middle of the data hub. From these blueprints, you can notice that there's governance, policies, monitoring, and all these type of things. And then your data catalog sits in your data hub. And when you create a new node, you basically instantiate that node from the central definition, and it operates according to the rules and the governance of the data hub. And queries are then moved backwards and forwards between the different data products in these areas. So notice here that they can also communicate with each other directly. So a data product, for example, you may have waste disposal that's dependent on citizen or commercial entity data. And so we could have a citizen master data system with a waste disposal system, and they could be communicating or agriculture and citizens, whichever two that you choose. And each of these areas have this concept of a data lake and a data warehouse. And one can then grow and extend this. Now, the reason why I say I think there's validity to it is because of this next area over here, which is edge computing. Now, lots of times people think, oh, why is this possible? Why is this required? You know, we all getting good bandwidth, but they're still saying that the latency that's caused between users and applications is causing inefficiencies and from a bandwidth and a throughput perspective. So we are saying that the users are still demanding that high level of efficiency. And I agree with that because I've certainly been reading in quite a few articles about companies almost buying, not almost, buying buildings right next to the German stock market, actually taking all of the floors out and whatever it is, and then rebuilding it with data centers that are so close to the stock market that they would get, they had no latency to the stock market, and the impact of that latency, microseconds as it was sufficient for them to justify building a data center right next to the stock market. Well, hopefully that the stock market had its own data center right there and it wasn't sitting in the cloud somewhere. But it is about moving the applications and data and edge devices and servers closer to the user. And again, there's been some fascinating articles of where to position these data centers all over the world to achieve this edge computing and to move these places closer and closer. So I think that's still an issue. So the mesh or the ability to distribute. I also see some interesting things with the Saudi government. They are consolidating their data in NIC data bank, but each ministry may have its own set of data products and data infrastructure. And would it not be a bad idea to build a mesh and connect them that way? HiveCell is on the is the competitive evolving product in edge computing. Yeah, and there's Databricks as well, Sheikh, that's doing some fantastic work in this area. There were some of the people that drew and put that together. This actually comes from, the diagram comes from Martin Fowler, who does a lot of work in terms of microservices. And he justifies this demand to have applications, everything developed according to the structure of the data, completely independently. So it wasn't about trying to get the same technology, the same approach for all products within the system. Okay. So that was a quick run through. We talk as well on the different schema issues where relational databases schema right. That means before I insert the data, I've got to have a table schema. Schema on read means there's no schema when I insert. I impose a schema when I read. Some great work happening there. I really like the implementation that SQL Server's done called Polybase. Sitting on top of relational databases, on top of graphs, sitting on top of document stores, sitting on top of Excel, Hadoop, wherever. And then this schema, which was, again, the type of Adabas Natural was the database that I first started working on, and it was tree structured. DB2 came along and made relational. And so that was an interesting learning curve. We used file system structures called ISAM VSAM, which is based or based on index structure. Okay, then we've got these other organizations: document, graph, key value, and column value. And we'll get to some of that a little bit later. But really just into document, the and then these aspects of the document. So the top type, then I have section, the two sections, and then section heading level 1, heading level 2, heading level 3, contained in those different areas. That's the way I like to try to describe it. And this is where I battled. And when I looked at this for a data citizen, I could not find anywhere in this context diagram to say this is where the data citizen would be, what the data citizen would be responsible for. Okay, other than providing requirements, that's sort of, there's nothing really that I could allocate to the data citizen to say you must do this work. Like I could do with a business glossary, I could do it with a data quality expectation. On all the other areas, the data citizen was missing in action. So that was my challenge. But one thing that I did realize, and this was specifically for Debbie, is that it doesn't matter what we're dealing with, whether we got Hadoop, whether you've got SQL, NoSQL, or NoSQL, we as data citizens need to be able to read all of our data. And we shouldn't be dependent on a DBA providing us with an interface. Or if we have data that's there, we should be able to access it and connect to it. Of course, given that we have the right access. So how do we read it? Or do we just put our documents into MongoDB and we forget about it because we don't know how to query MongoDB? So that's what this session is today, is trying to describe to you that it's not that hard. We don't need to be scared of these new technologies as they come along, and let's embrace them. Let's get as much as we can out of these different approaches. Now, okay, so now this is me just trying to show you the difference between and the reasons why these different structures came about. So we had SQL quite some time back. That was native SQL. It's ACID compliant, as we spoke about. We also had OLAP and OLTP, so we had analytical processing and online transaction processing. It was secure. We had application abundance, and workforce. Lots of people were able to work on SQL. One of the big strengths is that lots of our business users know how to write SQL. Even Johan does a fantastic job on SQL. Not so, sir. He's quiet.
I'm not going to put myself out there for the competition, so yeah, I can still help myself. Thanks, Howard.
Okay, yeah, Johan does a great job. I met him and he was a VBA expert. Since then, he's been doing SQL and R and Python, so it's nice to see that. There is a question there. So we have Kimball's law and dimensional modeling in the past. Is it diminishing in the modern data architecture? Yes, it is, certainly. And I'll show you some of the, so for example, whenever we're querying some of that high-speed data that's coming in the streaming layer, because and I think the big drive, Sheikh, is that we just can't wait for the data. The latency is becoming unacceptable, so we need to be able to query that. But there's still that batch layer that should go into the dimensional model. So it's not dead, but we have to coexist, and so we need to live together. And then we went from SQL, everyone ran away to NoSQL. And just to share with everyone that NoSQL doesn't mean there's no SQL. It actually means not only SQL. And that's another thing for you guys not to stress too much about is even MongoDB provides a SQL interface. And I've got MongoDB downloaded and I can do a select star and it gives me a SQL interface and it also gives me a document interface. And I'll show you the differences. But once you learn one, what I do find interesting about NoSQL is it doesn't allow linking. So you're not in a joining between documents and database collections, and we'll take you through some of that. Then we got, so there it was open source, it focused on scalability, it needed to ingest unstructured data, large data sets, performance, and fault tolerance. Then we went on to NoSQL that tried to marry the relationship between SQL and NoSQL. So there you can see it supports native SQL, it has the scalability, it has the transactions, and it's fault tolerant performance in large data sets. So fantastic. Also look at what's happened in terms of a structure point of view. You can see the problem with SQL is due to all the queuing of those transactions in isolation, we had to add more high-end servers. and of course your disk and your speed of disks are really costly. You can't just go into the latest or the Virgin Mobile Megastore and buy 3 terabytes of disk and put it into your high-end SQL service. They don't perform fast enough and they don't have the right level of fault tolerance. There we can see NoSQL coming along, building the data lakes, and we just got what they refer to as commodity services. So they can just add different servers. NewSQL comes along, brings the combination, high-end servers plus machines, and Hadoop is down the bottom here, which just is very similar to NoSQL. Now, Hadoop is more focused on your analytical side, and we'll show you some examples of that. Raj, can you please name some companies' products on NewSQL? I've actually got a slide for you. Fantastic question, Raj. We'll look at some of that right now. Okay. And what would it look like in terms of multi-parallel processing and cloud DBs? Okay, got some technology slides or product slides coming right now. Okay, so here is almost a view from a database management point of view, relational versus non-relational. So here are for you, Raj. Here we got user shared MySQL. MySQL is fantastic. MySQL does an amazing job of being able to change the engine underneath and make it run on traditional SQL, NewSQL, NoSQL, ISAM. It's fantastic what it does. I really like that architecture. Clustrix, see there, it's on disk, in memory, and on Hadoop. It's got splice machine. So it's sitting across multiple storage layers, NewSQL. There's our traditional SQL. And of course, we must remember that Oracle, SQL Server, these guys, they actually run it with, they can embed or ingest documents as well. It's not just limited. They've also got graph databases. So when we look at this, we will see that both Microsoft and Oracle have to start to pay attention to the wider range of storage approaches because they have value. The old idea of trying to fit thousands of documents into a relational table just doesn't work. And I remember I saw Niels on the line. I remember sitting with him and having these hundreds and hundreds of gigabytes of databases that took lots and lots of hours to back up, and it was hard to work with. Okay, so here's just a map of those different areas. We've got relational, Teradata, Netezza, Oracle, Amazon Redshift, but all sitting at MPP. Raj, I hope that answers a lot of your questions. Okay, so nice different areas here in terms of the breakdown. And then this was also nice to be able to flip it and say, what sort of databases would I use operationally and then what would I use analytically? And here we can see operational, NoSQL. I've got a document store, the document DB, there's MongoDB. That's been used tremendously by some of the big retailers. Amazon, there was a fantastic story that they presented on why they built the document DB, why they left relational. And I think they started off with MySQL, if I'm not incorrect. Then we have a key value store. There's table structures, column value store, Cassandra. There we've got our relational databases that most of us are aware, and then we have our relational analytics. And there's the Hadoop big data analytics. And these are the things that are put on Azure. So you can find them on Azure. Okay. All right. So now this to me has been fascinating in terms of in 2011 we came along and everyone started jumping onto the Hadoop NoSQL databases. Then the cloud came along, and we actually seen companies like Hadoop starting to battle. I can't tell you the exact reason, but some of the articles I've read is basically saying that the cloud was able to achieve the scaling that Hadoop was promising, and the cloud was allowed the customers to scale at the level that they needed to scale. And if we notice some of these percentages, SQL Server 57, MySQL 40, Oracle 38, DB2 14, and PostgreSQL sitting at 13. Here's another interesting database. There's some fascinating geospatial abilities that it has. And then here is our our NoSQL databases with Mongo sitting at 10. So they're relatively low. These things are changing on a constant basis, so please don't think that these statistics are up to date. This is what I've seen, what I've been able to pick up. And for me, what I'm trying to help with the data citizens and trying to get them to learn these different types of query languages to read the data is to really impress upon you that it's all dependent on the type of data that you're going to be working with. So if you need to analyze unstructured data, well, you're going to have to find the right DBMS to get that in, to be able to query on it, and also semi-structured, and then learn the appropriate query language there. And what I am seeing is so many of the vendors are putting SQL on top of that to help us migrate. And this was a nice slide, and I really enjoyed it in terms of helping us take the decisions, move through the process. Public cloud, yeah, that is a challenge at the moment, but Sheikh, I do believe that's changing tremendously with the new Sadaya data strategy and bringing on a lot of AI and bringing that into, and they're actually talking, if I remember correctly, they're talking to Amazon and that to bring it in. So I do believe that that's going to change quite a lot, bringing public cloud in. Okay, so we have heard discussions that they're underway at the moment. All right, sorry for that. I just jumped to that question. So what is the first thing to do? The first thing we got to do from a citizen point of view is understand the data type. Now, many years ago, before 2011, we were sticking big documents, they called it blobs. We were sticking documents into relational tables. It wasn't very pleasant. We had some serious storage challenges there. We used the binary max and we shoved everything in. Okay. Data type first of all. So there we see structured, unstructured, and semi-structured. And let's go the next step. And then it's what is the use case that you need for your data? And this was really comprehensive to see for asset transactions, OLTP relational. That's where you want to be. For analytical, you want to be in these column stores. Okay, guys, if you've seen this column store stuff, you've seen Microsoft Excel change to columnar, whatever you will call it. The column stores within SQL Server to improve the speed at which these applications return back to you. So make your choice. Don't think that relational is the only way. And this columnar, part of the problem that it had in the beginning was that once you processed the columns, you couldn't update it. And you had to update it the next day, or you had to reprocess it before it got updated. So that was, it has a level of latency. Now, I do believe some of those changes are coming about. Now let's look at semi-structured. And notice we've got a dictionary type of approach, and that would be key valued or sitting in memory, which is also a cache in memory. A lot of our databases, when we go in there, when we have an in-memory aspect to it, we use the hashing and the cache. Then we've got a 2D, two-dimensional key value. Okay, so then we've got wide columns, and so here now the use cases. Either I've got a wide column, or Johan, how's this? There's some really amazing time series databases that focus on specifically formats for time series. And I'd love to talk to the econometricians and Don about showing and having a look at this.
Question too.
Have you got a question as well? What is your question?
Where does dimensional fit in?
In OLAP. See columnar?
Columnar.
On analytics.
Okay.
So remember, dimensional is relational. And then columnar, when they bring it into memory in the memory things, then they're storing it in that columnar sort of thing. Okay, so 2D key value wide column time series. Then we've also got this immutable ledger. Okay, so that's where you can't change it. It's not just audit trail. I mean, we're seeing that on Bitcoin as well. And then we've got location and geo entities. Okay, geospatial. And then we've also got entity relationships, and this is fantastic as well. So yesterday when we were looking at John Gorman was talking to us about this graph. He said one of the best ways to do it is to go from your relational database into a graph database and then connect it to your documents and to bring the world together via the graph database. So also a really exciting development happening there and connecting to our relational database. Then we've got these nested objects, and I like the nested objects because one may be tempted to think that, so this is those higher levels, just the levels that we're structuring on. And there we have XML and JSON, and it's stored away as a JSON document. Sheikh, maybe just to stop here, I'm not sure. Are you asking for an example of time series database for telemetry use cases? Okay, so let's take you through some of the examples, and I hope that I can answer your question as we go. But I do believe we've got some answers for you. The next one is full text search, and we've seen that as well, where you can almost build thesauruses and language maps on top of text columns that allowed you to do text search, rich text. Okay, and then here we go down the bottom. Notice there's unstructured, and that's a blob. Basically, we take the entire thing, a video, an audio, and we can start extracting data. So these are our use cases. What would we use data? And I'm hoping that I'm providing enough background for you to say, let's not force everything into a relational database just because we understand it. Let's rather choose the right database and then choose how we query the data and read the data into from those different databases. And then the next step that you've got to do, and this is probably the hardest, which is choosing where do you go. And I did mention in last week's discussion that we're now finding so many of these hybrid vendors that are coming along that are actually putting a level on top of this where they allow you to go multi-cloud and on-site. Okay, so certain applications they're saying is just crazy to put on the cloud, and it's better on-site. So we now get these vendors that are supporting everything. And I've certainly seen SQL do that, where it allows you to install here and then stretch up into the cloud. Okay, so let's just talk through this. We've got all these different providers. Here we can see the geolocation. Notice this where Postgres also comes in. I'm not sure why they're not in this area over here. These are cloud agnostics. So you can see all the main servers. There you see Snowflake. Snowflake's predominantly in the analytical area. Okay, now that's not to say you can't put applications on, but it's really impressive in terms of what it's doing at an analytical side and sharing data. And here you can see all the different approaches. So for a wide column, you'd use a key space or Cassandra. For a document DB, now notice you've got Amazon, you've got Microsoft, Google, and then you have nothing to these edges that you install machines on site. These databases you're going to keep we've been learning. Okay, let's learn how to operate. Okay, so let's do the scenario where we've got when would we choose between SQL and NoSQL? So the pros of a relational data model: easy to use and set up. Yep, university compatible with many tools. That's certainly a big thing. Good at high performance workloads, good at structured data. Cons: time consuming to understand and also to maintain. It can be difficult to scale. It can be, but certainly with professionals that are out there, like Ramesh that was just saying had a hectic week as a DBA. These things can scale. We mustn't underestimate what the cloud vendors are doing with it. And so I think that the speed sometimes is not as big as the structure of the data. We have a document data model, also really interesting. No investment to design the model. Now, I'm not sure whether that's a good thing, but it is helpful. Rapid development life cycles, I've seen the sort of sprints getting in there where they don't have any design data modeling before the implementation phase. And interestingly enough, they're installing the data modeling tools on production, where those data modeling tools will read the database and then build a data model from the database and then tell everybody what data they have in the database, which is exciting. Okay, then we cons, it's unsuited for interconnected data. Now, that's also not true. I've seen Mark Logic, and I think it was on the last slide. Mark Logic is implementing, no, it's on the next slide. Mark Logic is implementing joins and interconnected schemas. So one of the things that they found is the documents were getting too big, and they wanted a master data connection so they could have all the customer data in another document and several sets of documents. Okay, so I think that's changing as well. So notice, so here is MongoDB. I like using MongoDB to just explain the document database. So let's look at the corresponding terminology. Both of them have a database. Now, in MongoDB, it has a collection, whereas in SQL, it has tables. In MongoDB, it has a document where we have rows. Now, we as users, we interface with the JSON document, but it stores it into a binary format. So it calls it BSON under the covers, but that's for compression and things like that. Then we have columns and they have fields. Okay, so hopefully that starts to give you a mapping between these two different technologies. Okay. All right, so here's a better definition. A MongoDB database, it's a container for holding document collections. Each database is associated with its own set of files, very similar to SQL Server. As you install a database, you allocate a set of files when you add the first collection. So the database does not physically exist until you add that collection. Interesting. A collection is a grouping of documents in a common namespace. So when you're having multiple namespaces, and we've seen that happen, so if my customer is getting too big and I want to then separate it, I could then have an employee's namespace and a leave or a learning or an education namespace, and we can connect the two via that. There's the document coming through. This is a basic unit of data in a MongoDB database, and so it only has one primary key, and that's the ID of the document. It doesn't have a primary key within the document. So we don't get into all of those design issues up front. And please don't get me wrong, I'm not saying those design issues are not needed. I think we do need them, but it does slow us down. Okay, so before I go into some of the query, I just want to show you typically what happens within a database. We have an interface language. That interface language, and it can be an API as well with a microservice. It allows us to define objects. So that was our DDL. It allows us to manipulate objects, which is a DML. That's your CRUD, create, read, update, and delete. And then there's different queries and control features. So we issue our SQL query or our NoSQL query to the query processor. It then uses metadata, and notice this is actually happening on both, whether it's SQL or NoSQL. It then chooses the path and how to get to the data with the indexing, then gets to the storage, and there's also metadata that it can update. Okay, so it can build a query plan using the metadata, and the indexes issues the update, whatever it is, and then in a way can rebuild the query, the index definitions and the statistics. Okay, so maybe just a simple slide. I like the slide to explain this columnar database that I refer to this. And notice this is the difference between OLTP versus OLAP. So here we have a logical table. and it's got a set of rows, and in there's 3 columns: date, product, and sales. Now, when you go into OLTP or relational, it stores it record 1, record 2, record 3, record 4 into a block. And a block is typically 8K. You can change it, but then each time you go over the block, then each time you get longer, then you create another block, and your IO level is happening at a block level. So you are very keen, and you have to pay attention to the right design choice for a primary key to be ever increasing, so that you had your records structured as nicely as possible. Okay, that's OLTP or relational. Rows are stored together, so you can see these are in one block. This is my contiguous storage. That's what it looks like. Now this didn't have the great performance that we needed, but it was helpful for small updates. And there we can see it's suitable for critical CRUD, right? Create, read, update, and delete. With this column or columnar was not like that. It was read only for quite some time. And there we see us storing our data and using chunking and hashing to get better storage. So there we had all of the column 1 data sitting together, all of the column 2 data sitting together, and all of the column 3 data. Now, the amazing thing about this was, for example, if we had 8 values in our domain for a specific table, we only needed a byte to represent all of the possible options that could go into the table. So we got massive compressions in this, and Excel does a fantastic job. That's when it broke some of those limitations of look, the 655361 one was really just a byte used to determine the number of rows that you had, so that really wasn't the columnar. But then it went on to 101 million that it's sitting at the moment. And I keep saying to people, do yourself a favor, rename the XLSX to a .zip file. If you open up that, you can see the .cub files, and you can see some of the techniques that it uses to get the chunking and the storage together. Okay, that wasn't really part of the discussion, but thought it was of interest. So notice here we got this comparison again: relational, SQL, non-relational. That's our model. We have structured tables. We have semi-structured data in NoSQL. See, there's key value, wide column, document, and graph. Flexibility, very rigid structure, and that's something that helps when we're using the transactions. Dynamic schema, ACID, mostly base, but we're getting a few of them are ACID. Consistency, it's strong. Now, because we're able to have some level of transaction within a non-document database, we can go from eventual to strong. So if we need strong, we can get there. And that's sort of where NewSQL is coming in to do a lot of that. Availability, consistency prioritized, where NoSQL prioritizes availability. Scale, so typically SQL does a relational goes up a vertically scale, and NoSQL does this horizontal scale. Now, I always battle with this because I know as a SQL DBA, we can create partitions, we can create always on, we can achieve that level of scaling, but I do know that the cost of the scaling is really extensive, and especially when we had to go and buy enterprise SQL before we got some of the scaling required. So for me, a lot of times it was about cost, and we could certainly achieve the scaling that was required, both vertically and horizontally. So I'm always puzzled with when they say SQL's only vertical. But anyway, maybe it's on one server. Okay, so here, this is where we start programming. That's something that I really MongoDB, you have to operate in this format. I'm just saying that if you wanted to operate in native MongoDB, this is how you would do it. Okay, so in in normal SQL, we would just go insert into employees, employee ID and age, and we would give it these values. Whereas in MongoDB, we just say db.employees.insert, and it would say this is my employee ID. And notice this is the JSON document structure coming out here. This from the bracket to the bracket, and you'll see more of that coming through. But what was important is that the relational side, if you didn't create that table, you would certainly have a failure when you tried to do an insert, whereas this wouldn't be the case within MongoDB. It would then actually set up your files and everything when you did that insert. Okay, so looks very similar. I mean, is one really harder or easier than the other? I don't believe so. It looks pretty straightforward. Now, here's a great example of a key value pair. Notice here's the key, 746133. It means nothing other than it's the ID of a document. And within the document, I've got first name, last name, and product ID. And notice that the product ID across the different keys are changing. And this is one of the benefits that we see now, where that structure, or we could have arrays within columns within NoSQL, whereas that typically wasn't allowed. We had to sort of build this ourselves, and we were really naughty if we put in these multiple fields within one field. But there's a nice structure. Notice within the product ID, this has actually got two products, 1285 and 1077. So you could have an array of products, but great for things like order documents that have order lines, and you would just keep on adding elements to that one document. Whereas this would have multiple tables and lookups and all sorts of stuff. But look at the SQL again. Okay, again, it's oversimplified, but it says select star from customer table where last name is equal to Smith. We know that. Now here is NoSQL. It's just a get customer.first name, last name, customer.product ID star, give me all of those where last name is equal to Whitlock, sorry. Okay, so not very complicated, is it? There we read the data. This one is pretty complicated, and I just wanted to show you this just to give you an idea. I know it looks hectic, but so this, for example, is what we would use. Remember, this is like a, sorry for the formatting, it was pretty lousy, but this would be an aggregation, right? We would write a query like this when we want to aggregate our data set, and there we see ourselves selecting off a denormalized aggregator table, and we group it by dimension 1, dimension 2, and then we'd have these sums. Okay, and we could have all sorts of logic in here, but then we could also filter with having greater than 0, order by, record count, a typical SQL. Okay, now when we move into MongoDB, and this is also MapReduce, so MongoDB supports a MapReduce, and what's amazing now is that you can write the SQL query, and then you can go to Mongo and say, translate it into MapReduce. Remember, Hadoop had this with MapReduce, Pig, and Hive, so they had this format, and this is now what MapReduce looks like. And it's very much of a programming language, and I'm sure all the programmers around here could work it out. There's our query. These are the filters where that must be in A and B. This is the table that we're going for, the collection. We must filter 2 is on C, and then the other filter is greater than 1, 2, 3. And then we build the functions that return our value. And notice what we're doing is we have all of the data within that, and we're doing a for loop, and we're summing or adding the value together, and unless it's less than, and as long as it remains less than or less than 100. And we're really just incrementing it. We've got a for loop. This sort of looks like VBA, and it's a pity Johan left, but this was almost like a VBA. This is how we would code the same thing in Visual Basic in Excel when we wanted to automate Excel. And notice here we finalize, we just say, once all of these calculations have been done, then return the value. Okay, and these are some of the results, and there we can find and sort and skip and insert That's how we achieve a similar mapping to that of SQL. Okay, update, also pretty easy. Here's update SQL, update employee, set employee name to new Martin where employee ID equals 1. Well, look at MongoDB, update employee ID 1. So inside of this, you've got a JSON document inside of it, and you're issuing it to the database to query, and there you're saying set employee name to new Martin. Now, if I wanted to update all of the documents, this is the update command that we do. Now I'm updating both employee name and new Martin and employee ID 22. So you could send your Mongo queries via a JSON document, which is also quite nice to keep that consistency. Here is a delete invoice.remove. Pretty simple. There's no conditions here. I can delete all of the documents from a collection, or if I wanted to delete a specific document, then I would say remove where the order quantity is greater than 100 and just only allow a single delete. Okay. So there we had the read, create, read, update, and delete. These are references as to where I got all my reference material, and that pretty much brings me to the end of my presentation for today. So I was hoping that you learned a lot, that you could see that it wasn't as complicated as we thought. Hopefully, I thought, and I keep on saying that we can do this. We can see everybody's stuff. Any questions? Any observations? Comments?
Thank you very much. It was absolutely fantastic presentation. And I had a few questions on where actually you will start implementing the data quality checks. In which story you will be trying to do a data quality checks.
Okay, that's a good question. So that's part of the problem that we know when we're relational, then a lot of the data model can help our data quality checks. So excellent spot there. Whereas if we go into document DB, you insert it and there's nothing there that's going to do that data quality check for you. What I have seen, Sheikh, however, is that is in building machine learning algorithms that go through the different elements within the data lake and detecting the quality of the documents within the data lake. And they're having all of these different indexes and collection elements that are able to provide data quality. Where I believe you would do it is when you build those views or the data marts on top of that unstructured data. And then you'd have it very similar to that of the data warehouse. Even today in our life that we have today is where some data can't come into the data mart or the data warehouse because of certain quality issues, and it will then get left in the lake or in the different areas. So you'd probably focus a lot of your quality on the ETL into the warehouse and the warehouse itself, or from the warehouse down to the data mart in that scenario. That doesn't answer the question in terms of how would applications enforce the data quality. It's a good question. I'm not exactly sure, other than sort of doing what I've done in some cases where you build a data quality firewall where you could get elements to read the database from a unstructured or document format into more of a table format to enforce the rules and see what breaks at that time, and then build a report on your quality issue. That would probably be my approach.
Yeah. So why I asked this question is for one of the telco customer whom I was evaluating their architecture, where they have NoSQL, Hadoop, and all MPP databases. They were just dumping the data for 3 long years, and they were unsure about what data is being stored on their data store, probably in HDFS. So that's where I just got into is this data quality checks needs to be applied even the data gets ingested into the data lake, or it's an after it's an after process when the data is in the data lake and then we need to do a data quality.
Right. So I can certainly give you we actually had a presentation from a guy, Guillermo, who focuses on data quality on data lake using machine learning algorithms that they run across all the data and then give you almost a data quality rating of your data in a data lake. So fantastic work there. If you are interested, I'd be happy to share his details with you. And show you all of the stuff he's written.
Thank you.
Excellent. Send me an email or contact me on LinkedIn or Debbie, and we'll connect you up.
Sure.
Okay. So Raj, you're asking some clarity on the bus architecture of Ralph Kimball. So what you'll find, Raj, and I'm not sure if you always, whether we're up to date with that almost that post side. So let me go back to that slide that we had with the data lake house. Those are some of the things that the reason that the lake house was introduced was to add, let's go back, here we go. So was to add the warehouse into the picture. So the data lake, right? The data lake is, it's immutable. So it's read once, you can't go and update it. And you have to apply some of the requirements that you're talking about into the data warehouse where it has this ETL processing area. Now, remember the difference, a data warehouse in Kimball, in RK's terminology, is a series of data marts. In Inman's terminology, it's the enterprise data warehouse. And so here you could have either or both. So you could have the enterprise using Data Vault, and then you could have the data marts that enforce the data quality off the Data Vault, and you can get data into this area approach using the appropriate processing and BI. So when we see data warehouse, read into that you'll see the data marts there as well, plus the bus architecture, the conform dimensions that give you the bus and the bus matrix. And so that comes in there as well. Raj, does that answer your question? And then, of course, you're going to have data ops, DevOps, data ops coming into this data warehouse area wherever you need to manage the structure and the schema. You're going to be doing it there. And one would also hope that you've got a master data system here that's providing your dimensions of your data warehouse that are also critical that you want to bring into this data warehouse as well. Okay. So I'm hoping that all of you are happy to program in NoSQL from now on. Especially Paul, and he's gone quiet. Where are you, Paul? Has Paul fallen off?
We have a storm.
I don't think so.
Okay, Debs, would you mind? I don't know if there are any more questions, or anyone have any questions before we wrap up and close the stop the recording. Do you want me to do that?
I can definitely do it. Jeff, if we don't have any more questions, or if you want to save your questions for afterwards, you can always drop Howard a message on LinkedIn. Yeah, thank you, Howard, and thank you everyone for the session today. I know we all learned a lot, and yeah, I really appreciate it. Thank you so much.